This course is Fundamentals of Telecommunications Part 1, and this is the first video course in the core training series. In this video, we're going to cover the public switch telephone network and plain ordinary telephone service. And before anybody starts saying, well, this is old stuff, we don't need to know this, it's all going to be voice over IP, well, take a look at this graphic. This is a picture of an adapter for voice over IP at a residence. And if we look at the back on the connectors here, well, we've got the power connector. We've got a jack to plug an Ethernet LAN cable into, so this is what the IP packets will go over. And what's sitting beside it? A plain ordinary telephone service jack. The whole idea with this adapter is you plug a regular telephone into it, and it acts pretty much like a computer and does all sorts of functions like voice digitization and packetization, and it runs the RTP protocol and SIP and all this stuff that you learn about in the voice over IP series. But it's got a POTS jack on it because the last 3 feet in this story goes to a regular telephone. So this discussion of POTS, not only does 99% of the network still run on plain ordinary telephone service, but even if we go to an all voice over IP story, there's still going to be countless POTS telephones plugged into adapters, and so you're going to have to know about POTS. And not only that, the history of telecommunications is all built on top of plain ordinary telephone service. So no matter what you want to understand, POTS is the place to start. Well, let's jump right in and get started with a basic model for the public switch telephone network, the PSTN. If I wanted to draw a picture of the PSTN, I'd probably start with a telephone. Telephones are connected to telephone switches using 2 copper wires. Some jargon and buzzwords you'll probably hear. The building that contains the telephone switch is called a central office. And the building that contains the telephone is called a customer premise. So you could call the telephone a piece of customer premise equipment if you really wanted to. When I first started working in this business, I was never really sure about the word premise nor how to spell it. And I didn't have a spelling checker on my computer, so I had to actually go down to the library and get out a book that lists all of the words in the language and how to spell them and what they mean, and look up the word premise. And it turns out that it comes from British real estate law, and what we're discussing is the contract of sale of an immovable good, a building, and the building is the premise of the contract. Therefore, if you have one building, it is a customer premise. If you have 2 buildings, they are customer premises. This is the most commonly made mistake in the telephone business, is referring to a single building as a customer premises. Wrong. Everybody makes this mistake. You hear cops on TV shows saying the suspect was on the premises. No, the suspect was on the premise. Unless the suspect walked from one building to another, then they were on the premises. Does me good to get these things off my chest. The 2 wires that are used to connect the telephone to the telephone switch are called a loop. And you'll also hear it called a subscriber loop or a serving loop or a local loop. But most of the time, they're just called a loop. Why do we call them a loop? Well, it comes down to the question of how do you indicate from the telephone to the telephone switch that you, as a user, want to start communicating. What do? Sometimes people say pick up the phone, and then I can say, well, just picking up the whole phone doesn't do anything. You have to pick up the handset and leave the rest on the table. That's called going off hook, because the handset used to actually be on a hook. Inside the telephone, there's a little switch, and I mean interrupter kind of switch, that's normally open. So those two wires that are connecting the telephone to the telephone switch are normally not connected together. And when you go off hook, the little switch closes, connecting the two wires together. Now over on the telephone switch, the thing that terminates the two wires is called a line card. This is a little module of electronics. Often there are a bunch of them on a card and they plug into drawers that slide in, and there are racks and racks and racks of them that make up a telephone switch. But it's a little collection of electronics, and one of the functions of that line card is to put voltage across the two wires. And voltage is like pressure. This is the thing that can force electricity to move around. And for those of you like details, it's minus 48 volts. Now, when you're on hook, the little switch inside your telephone is open. When you go off hook, the switch closes, and at that point, the voltage that the line card is putting across the two wires can then succeed in pushing electricity or electrons around in a circle or in a loop. This is why they're called loops. And what we're discussing here is called supervision. Supervision means regardless of to whom you wish to speak, and regardless of what you're going to say to them, how do you indicate to this switch you want to start doing all of this stuff? And this is called loop start signaling. You close the little switch in the telephone, and then current can flow around in a loop on the two wires. Now over at the line card, they can tell that you closed your little switch to start current flowing around because they've got a relay. And what a relay is a switch with an electromagnet. Did you ever fool around in grade school with magnets and pieces of paper and iron filings? And if you wrapped a wire around the magnet and then connected to a battery, the magnet worked a lot better? Well, that's what a relay is. The two wires, which are the loop, would actually be wrapped around a magnet, and then there's a switch sitting on top of it, and when the electricity starts flowing through the wires, the magnet would pull the switch closed. So they can tell on the line card that you closed your little switch on the telephone and started electricity flowing around in a loop. That's how you indicate from the telephone to the switch you want to start communicating. How does the switch acknowledge that request to start communicating? Well, they put a dial tone on the line. Assuming you've paid your bill recently, of course. Now that's half of the supervision. We have to talk later about how the switch indicates to the telephone that it's the switch wants to start communicating. We'll go through those details in an upcoming discussion on details of plain ordinary telephone service. If you want to talk to someone, they have to have all the same stuff. They have to have a telephone. It's connected to a telephone switch using two copper wires. And if they live far enough away from you, they're going to be connected to a switch in a different central office building. And they don't live with you, so they have their own customer premise. These loops are dedicated access lines into the telephone network. You most likely have two copper wires that go from your place to your nearest telephone company's central office just for you. Nobody else uses those wires. I've got wires that go from my place to my nearest telephone company's central office. Nobody else uses these. These are dedicated access lines. Now the connections within the network, in other words the things that connect switches together, these are not dedicated for you to talk to me. Like we don't have a hotline between our houses. These things are shared, and they are called, of course, trunks. Let's keep things simple. Loops are things that connect telephones to switches. Trunks are things that connect switches together. Any other use of those terms is probably not correct. The service that we normally offer residential customers on top of this network is called POTS, Plain Ordinary Telephone Service. It's also referred to as dial tone, and if you go visit your local regulator, you'll probably see it called Individual Residence Line Access Tariff or something silly like that. But most people call it POTS, Plain Ordinary Telephone Service. And the way that this service works, if you want to talk to me First, you have to tell the switch you want to start doing all this stuff. Then you have to tell the switch what my network address is. You call them phone numbers, I call them network addresses. And then the network, in other words the switch, is going to have to make a routing decision. It's going to have to decide which trunk circuit to use to get to this network address. And there could be literally 10,000 trunk circuits going out of this switch. It's got to pick one of those and reserve it for this phone call. It's called seizing the trunk. Now this gets us down to the far end central office. We have to indicate the called number to the far end switch, because it has to determine which pair of wires, which loop to connect us to. And there could literally be 100,000 loops on that switch, and it has to connect us to just one of those. Now once we've got this all set up, where we've got the dedicated access line, connection through the switch, connection over a reserved trunk circuit, connection through the switch in the far end, and then the dedicated access line at the far end, then we've got a live interface connection, and we can do whatever we want for as long as we want until one end or the other hangs up, and then that trunk circuit in the middle is released for somebody else to use to go between those two central offices. This technique of establishing connections across a network is called circuit switching. Dedicated access line here, dedicated access line there, trunk circuit switched in to make an end-to-end path for the duration of the communication session, and then released. You'll also hear this called dial-up. But I don't have any dials on my telephones. Do you have any dials on your telephones? No, circuit switching is the correct term for this. It's one of the three ways of establishing communications across a network, and we're certainly going to cover all three during this core training series. Just to give you a quick preview, the other two methods are called dedicated lines, where we have a permanent connection, and packet switching, where you don't have a reserved connection in the middle. You just send stuff into the network and it gets forwarded on a best efforts basis and not necessarily any reserved capacity. But we'll go through all that stuff later on. An important point here is that there's a maximum length allowed for the loop, which is usually 18,000 feet, about 3 miles or 5 kilometers. And the reason why there's a maximum length allowed is because we use copper wires to implement the loop. Why do we use copper? Well, because it's cheap and it's easy to make wires out of copper. And it doesn't rust very much, and if you bend it in the wind, it doesn't break. And it's a pretty good conductor of electricity. But it's not a perfect conductor of electricity. Gold is a much better conductor of electricity than copper is. But if we started using gold for telephone wires, well, you can fill in the blanks on that one. Actually, it turns out that silver is a much better conductor of electricity than either copper or gold. But anybody who has ever had to polish sterling silver will attest to the fact that silver rusts, it oxidizes, so it's not very useful for electronics. So we use copper. Because of the fact that copper is not a perfect conductor of electricity, it has some resistance to the flow of electrons through it, what's going to happen is that this resistance is going to slow down some of the electrons. Think of swimming through molasses here. And it'll change their kinetic energy into heat. And the voltage on the wires will drop because of this effect. Now, I don't mean that the telephone wires heat up, but actually, have you ever noticed a hairdryer cord does? Because you're pumping so much electricity through that cord, the resistance in the wires actually heats up the cord. Those things on top of your stove that turn red, those are resistive elements, or trying to turn all of the energy into heat. On a copper wire loop, we're trying not to do that, but we're not 100% successful. And what you would see is if you measure the voltage on the wires near the line card, which is the thing that's putting the energy on the wires, and then you went further down the loop and you measured the voltage at different points down the loop, you'd see the voltage get smaller and smaller and smaller and smaller. and this effect is called attenuation. It's the diminishment of the signal with distance because of the resistance of the wires. The length of the wires is actually specified as a maximum allowed resistance, but with the thickness of wires that we normally use, it works out to 18,000 feet is the maximum allowed length of the local loop. Let's do a quick history lesson to better understand the geographical topology of the telephone network. The telephone, as we know it today, was patented in 1876 by Alexander Graham Bell. And beginning in the 1880s, local telephone companies started to be established. And the reason why there were local telephone companies is because of this 3-mile limitation on the distance you could communicate between the central and the telephone. So in each major city, some organization, whether they were owned by Bell or friends of Bell or they were paying them royalties, would get some equipment and put it in a building called a central or a central office, and then sign up subscribers to this fancy new communication system and connect the subscribers to the central office using copper wires. So the model was we'd have one building with a serving radius of about 3 miles around it. And that was it. So we had local telephone companies in each city. And then we started looking at how we would connect these together. And for example, AT&T was incorporated in 1885. And their initial business model was that they were going to be a long-distance company only, and they would connect these local companies together so you could do interurban communications. This diagram is a model of what the telephone network looked like up until the end of the Second World War. After the Second World War ended, Al Gore's father invented the interstate highway system, and everybody moved out of downtown. Suburbs happened. We see those pictures in Life magazine of Tarrytown, New Jersey with all the cookie cutter houses. That all happened after the Second World War. Now, let's say that some developer buys a farm and bribes some local politicians to change the zoning from agricultural to residential, and then they build 350 homes on this farm. And all of the people in these homes want to get a dial tone. But the nearest central office is 15 miles away. How do we give all of these people a dial tone? Well, we could use special thick wires, which have lower resistance so they can be longer, but that's real expensive and difficult to manage. Another thing we could do would be to build a central office for 350 people. That sounds kind of expensive. The solution is to put a little baby telephone switch called a remote inside a concrete box and bury it in the ground. This concrete box is called a controlled environment vault. It provides light and heating and humidity control, and it would have all sorts of power equipment in there, and it would have the little baby switch called the remote sitting there nice protected inside this concrete box. And the concrete box has a person hole, and if you're driving along the street and you see the telephone crew there and they've got a tent over the manhole, well, what they're doing is they're protecting the equipment in the controlled environment vault. And if you actually get out of your car and go peer down the hole, you'll see their ladders, and it's a room down there with lights in it. And what we can do is put one of these things on the edge of the new subdivision and then use regular loops with a maximum length of 3 miles to give everybody in the subdivision a dial tone. And then we connect the remote inside this controlled environment vault back to the nearest big central office with an umbilical cord called a loop carrier system. The reason why it's called a loop carrier system is in the simplest implementation, it's not adding any value into the story. It's just taking whatever is on the loops in the subdivision and backhauling it back to the nearest big central office. And all of the decisions would be made there. Now, as soon as I say that, the implication being if somebody in the subdivision called their neighbor, the phone call would get carried back to the central office, switched there, and then all the way back to the subdivision. And you might think, well, wouldn't it be smarter to have some local capabilities inside that remote? So if somebody called their neighbor, it was switched locally rather than being backhauled all the way to the central office? And the answer is yes, but we like to keep these remotes as dumb as possible. The reason? Money, as usual. We do not want to deploy all sorts of fancy software on these remotes, because what that would mean is every time the software is upgraded, we'd have to go patch the software on thousands of remotes. No. We want to have all the fancy stuff and the technicians, the people in the central offices, and have these remotes as dumb and not personed as possible. So what we'll find is that a telephone company for a medium-sized city will define 3 or 4 COs as the big COs in this city, and all of the remotes will home into one of these big COs, and the technicians and the people and the expensive stuff will be in the COs. The loop carrier system, originally these things were coaxial cables. We had the Slick 96 from AT&T, the subscriber loop carrier, and it could carry 96 separate loops on one coaxial copper cable. For a while we were using point-to-point radio systems as loop carrier systems. Most of the time now it would be fiber. So that loop carrier system would be implemented using a fiber connecting the remote back to the nearest big central office. Now it depends whose numbers you believe, but between 30 and 50% of telephones in North America are connected to remotes. If you live downtown in a city, chances are real good you're hardwired to a central office. If you live in a suburb that's fairly new, chances are real good that you're connected to a remote and then it's backhauled over a loop carrier system back to a big central office. In theory, this doesn't make any difference, and for POTS, you wouldn't be able to tell the difference whether you have this or not. For some of the newer services, it might make a difference in terms of availability, like, for example, whether you can get DSL or not, and we're certainly going to talk about that in the DSL module. This is a basic model for the public switched telephone network, the PSTN, where we've got customer premises containing customer premise equipment, and the simplest kind is a telephone that supports POTS, plain ordinary telephone service. The telephone is connected to a telephone switch over a loop, and the loop is 2 copper wires with a maximum length of 3 miles or 5 kilometers. If you're more than 3 miles away from a CO, chances are pretty good you're connected onto a remote, and then the information that's on your loop gets carried over a loop carrier system back to the central office. The way that phone calls are established, a trunk circuit connecting your central office to the central office of the person to whom you wish to speak is reserved for the duration of your phone call. The loops are dedicated access lines. The trunks are dedicated for you to use, but just during your phone call. And then when your phone call is over, the trunk is released for somebody else to use to go between these 2 central offices. This is called circuit switching. It used to be called dial-up. There are many aspects of the public switch telephone network and plain ordinary telephone service that we could discuss. We're going to try to pick out the most important ones. Probably the method used to represent information on those 2 copper wires that make up the loop is one of the most important ones. The way this works is that the user gets a handset, and in the handset there's a speaker and a microphone. And the type of microphone you get in a telephone has got a hard plastic housing and a paper diaphragm with some carbon particles in it. And the idea is, while I'm speaking, sound pressure waves are coming out of my face like this. So I hold the microphone up in front of my face, and the sound pressure waves hit the microphone and physically move the piece of paper back and forth, squeezing the carbon particles more and less. And when we squeeze the carbon particles, this changes their electrical characteristics. And we can use the fact that the electrical characteristics of the microphone are changing to make a voltage go up and down on the copper wires. And this voltage is a representation of the sound pressure waves coming out of the speaker's throat. And it's a direct representation. As the sound pressure wave starts hitting the microphone and pushes the piece of paper in, the voltage goes up. As it stops hitting the microphone, the voltage goes back to where it was. So we have a direct representation of electricity for sound pressure waves. What's another word for representation? Well, how about analog? Look up the term analog in the dictionary, you're going to find representation. Look up representation, you're going to find analog. We have the word analogous in the English language. If one thing is analogous to another, it's similar or representative. We have analogies. These are little stories that are representative of an idea. Here we're putting a voltage on the wires, which is a representation or an analog of the sound pressure waves coming out of the speaker's throat. So the voltage is the analog. People then stretch the terminology to refer to those two copper wires as an analog circuit. But that's not very precise. The only thing analog in this story is the method that we're using to represent the information. It would be more accurate to refer to the loop as two copper wires that were designed to be able to carry a voltage, which is an analog of the sound pressure waves coming out of the speaker's throat. But that takes a long time to say, so people call them analog circuits. Keep in mind that analog is the method we're using to represent information. We could use digital techniques on those same copper wires. I'm a systems engineer by trade, and I was trained at great pain and expense by companies like Nortel to say, well, hold on a minute. Let's just back off these half-baked ideas you have about how you want to build the thing. What do you want to do? Wouldn't it be better to get everybody to write down what they want to do and sign their name to it before we start building it? Because if you start doing it the other way around, building something without agreement on what it's supposed to be doing, you're going to end up wasting an awful lot of time and money. So if we back off from discussions of analogs and loops and trunks and circuit switching and consider what we're trying to do here, what is the purpose of building the telephone system? Well, to make money, yes, but besides those crass things, sometimes in class people will say to communicate speech. But I would claim that communicating speech is part of the design. What's the purpose of communicating speech? Is to communicate thoughts between people's brains. So the overall purpose of the telephone system is to communicate thoughts between people's brains. Now you might say, okay, well that's a nice noble objective to have, communicating thoughts between people's brains, but we have to actually start making some design decisions. Well, what we decided was to communicate thoughts between people's brains. We weren't going to try to do Vulcan mind melds. We were going to use speech and hearing. Now, if it was your job to determine what the characteristics of the local loop should be, knowing that we're building a system to communicate speech, well, you'd want to get a pretty good idea of what speech was. And if you got out a textbook and looked up speech, the textbook would first define speech as a type of sound, and then the next paragraph would say that sound is sound pressure waves in the air. Sound is air molecules getting closer together and then further apart. It's called compression and rarefaction, for those of you who like details. And it said that if this happens between 20 times a second and 20,000 times a second that it's said to be audible. That's the textbook definition of what sound is. Do you believe this? Well, I've got a question for the philosophers out there, and this is one of these annoying questions that you probably heard for the first time in grade 4, and you're never really sure what the answer is. The question is, if a tree falls in the forest and nobody's there to hear it, does it cause a sound? To decide whether the tree falling in the forest and nobody's there to hear it, does that cause a sound, you have to decide, is sound something that's defined as being out here? Is sound pressure waves in the air? Or is sound something that's in here? Is sound the sensation you get in your brain when you hear the sound pressure waves? And once you decide the answer to that question, then you can answer the first one. What's the answer to that question? Well, sorry, this is technology philosophies in a different series. You have to decide what the answer to that question is. What I'm getting at here is that when we build this electromechanical system for moving speech from one place to another, and then we wanted to test it to see if it worked or not, there would be two schools of thought as to how to design the acceptance tests. One group of people would say, well, what we're going to do is we're going to measure the sound pressure waves reproduced at the far end and compare them to the sound pressure waves coming out of the speaker's throat and see if they're the same or not. Another group of people would say, no, we're not going to measure that because it's not what we're trying to do. What we're going to do is measure the sensation that the listener gets in their brain and compare that to the sensation that they would get were they speaking directly to the other person, because that's what we're trying to do. And what's the difference between these two ideas? Well, the brain is a hugely complicated processing instrument, and you can play different stimuli at it and get the same response. So, what did A.G. Bell decide? Well, he picked answer B. Based on testing people's ears and brains and throats and some technical limitations at the time, Alexander Graham Bell decided that what we were going to do was transfer all of the information in the range of frequencies from 300 to 3300 hertz, and this is called the voice band. Now, I just used a whole bunch of buzzwords. Frequency is the rate at which things vibrate. The units for frequency are vibrations per second, or hertz. They were almost called avises, but hertz bit more for the rights. And this range of frequencies, or band of frequencies, is called the voice band. It starts at 300 and it ends at 3300. And what we're trying to illustrate in this graphic is that you can do whatever you want on a telephone line as long as you use electricity to express your emotions, and the electricity must vibrate at least 300 times a second and less often than 3,300 times a second. If you try to put electricity on a telephone line that vibrates more than 3,300 times a second, that gets suppressed. There are little electric filters in both the telephone and on the line card in the switch that suppress any electricity vibrating more often than 3,300 times a second. If you try to put energy on a telephone line that's vibrating less than 300 times a second, that gets suppressed. Only energy vibrating in between these numbers, 300 and 3,300, gets passed through the telephone system. The term bandwidth means capacity, and for our purposes these are synonyms. Bandwidth means capacity. And in the analog world, capacity is measured literally by the width of the frequency band you have to play with. So that would be 3,300 minus 300, so the width of the frequency band is 3,000 hertz wide. And of course we use kilos, an abbreviation for 1,000, so that's called a 3 kilohertz voice band channel. And this is a standard offering from every telephone company in the world. When you sign up for POTS, plain ordinary telephone service, this is what you get. Now, a question to ask here is, why does it stop at 3300 hertz? Are your ears and/or is your brain capable of detecting sound pressure waves that vibrate more often than 3300 times a second? Well, if you look at the specification page of your stereo's user manual, you usually see things like frequency range 20 to 20,000 hertz, because that's traditionally what the human hearing range is thought to be. And yes, a 5-year-old child might be able to detect sound pressure waves vibrating 20,000 times a second. I went to see Pink Floyd at the Olympic Stadium in Montreal, Canada in 1976, and I stood in front of the speakers. So I've got a bit of a high-frequency hearing loss, and I can't detect sound pressure waves vibrating 20,000 times a second. I can hear up to about 7,000 times a second. But still, this is way less than what I can hear. Are the wires, which make up the loop, capable of supporting electricity that vibrates more than 3,300 times a second? Yes. People are talking about electricity vibrating 1 million and 2 million times a second with these fancy new DSL services. So why would we restrict the capacity we allow a user to employ on an access circuit into a network, even though their brains and ears are capable of more than that, and the wires are capable of more than that? Well, answer number one, money. The more capacity we allow a user to employ on an access circuit, the more it's going to cost to transmit the information long distance. There's a direct relationship between the bandwidth on the access circuit and the cost to build a network to transmit that information. And the 3300 number was determined based on testing people's ears and brains and throats to figure out what the minimum was we could get away with. So to get back to our business of trees falling in the forest, we are not trying to reproduce the sound pressure waves at the far end exactly the same as the ones coming out of the speaker's throat. In fact, they're quite muffled and distorted. All the high frequencies have been chopped off, and it actually does sound like that, but we don't think it does because we listen to it so often on the telephone. What we're doing is we're reproducing the sound pressure waves just well enough that the listener can understand the words that the speaker is speaking and thus communicate information. This is a speech communication system. It was never designed for music on hold. Actually, 3300 hertz isn't quite enough. Have you ever noticed it's difficult to tell the difference between an S and an F over a telephone line? That's because the thing that distinguishes st from ft lives at about 5,000 hertz. If I go st or f, there are sound pressure waves coming out of my throat vibrating around 5,000 hertz. The telephone system does not transmit those. So if you go st or f, it comes out the other end sounding the same for both of them. So you have to say S as in Sierra and F as in Foxtrot to distinguish between S and F over a telephone line. And there's the whole phonetic alphabet. There's the one the military uses, and there's one for the International Telecommunications Union. I came up with my own. I like to confuse people by saying things like, that's G as in gnat, and K as in not. Or if you really want to confuse them, try saying that's S as in C, or E as in U. We could spend an entire course talking about plain ordinary telephone service. You could spend a whole week talking about POTS. You could spend a whole life talking about POTS, and some people do. We're just going to hit a few more of the high points to finish off this discussion. On this chart are a number of buzzwords. One of them is twisted pair. Now, what's going on here? Well, do you remember before cable TV, when you bought a television, you got rabbit ear antennas to watch VHF and a loop antenna for UHF. You'd actually plug a loop antenna into the back of your television and twist it around. Well, it turns out that the amount of energy that a loop antenna picks up is proportional to its area. So if you make the loop bigger, you get a fatter detected voltage on the antenna. So what we're going to do is connect up a 3-mile diameter loop antenna to the back of our telephone. Sound like a good idea? Not. Because if you did that and then picked up the handset and listened, all you'd hear is because the loop would act like a huge antenna and pick up all sorts of interference from things like radio broadcasts and spark plugs and microwave ovens and wireless LANs and things like that. To diminish the antenna effect of those two wires that make up the local loop for pots, we put plastic on them and then twist them together. Now, since there's plastic on the wires, after we twist them together, from an electrical point of view, it still just looks like a big current loop. But from a magnetic point of view, from a radio waves point of view, from an interference point of view, it ends up looking like a whole bunch of small loops when we twist it together. And you can show that the total area of the small loops is smaller than the area of the big loop. And so by twisting it together, it minimizes the antenna effect of the two wires. And since there are two wires, it's called twisted pair. We use twisted pair for just about everything these days. It's certainly used for all of the inside wiring for regular telephone service inside your home. All LAN cables these days are made of twisted pairs. And what are some other examples? Well, Hillary and Bill Clinton come to mind. This diagram is a block diagram of what's inside the telephone. At the right, we have a handset with a speaker and microphone, and at the left, we have two copper wires going off to the phone company, and in between are a number of different components. One thing that's important to note here is that the two wires that are the loop are used in both directions at the same time. It's not like there's one wire for transmit and another for receive. No, the voltage, which is the analog of the speech, is charged up and down on the wires like this. It's called balanced signaling. It works better for noise. And both the telephone is making this happen on the wires, representing the near end person speaking, and the line card is doing that at the same time on the same wires representing the far end person speaking. And those two voltages are added together. Like if you're looking at the ocean and you see two waves, when the waves collide, they add together like this. The same thing is going on a telephone line. Since there are a total of two wires going to the telephone company, but in the handset there's a speaker and a microphone, each of which requires a little loop, two wires, to make it run, there's a box called a hybrid or a hybrid transformer inside the telephone that does this 2-wire to 4-wire conversion inside the phone. So 2 wires off to the phone company on one side, 2 wires to run the speaker, and 2 wires to run the microphone on the other. And the hybrid is a little transformer and a couple of resistors and capacitors, and it sorts out what's coming and what's going. There's actually a little bit of energy fed back from microphone to speaker. You can hear yourself talking, and this is a psychological feedback mechanism to limit how loudly you speak on the phone. You know how people wearing Walkmans tend to shout? It's because they can't hear themselves normally, so they start talking more loudly. When I hear people shouting into their cell phones, I always feel like saying, "Would you please turn your side tone up?" Because side tone is the word for the feedback that you get in your ear. And what's happened is the person's turned the volume on their cell phone down too low, so they don't hear themselves, so they start shouting into their phone. If they turned the volume up, they'd get much quieter. On most phones, you can't regulate the volume, and so we all talk at the same level. But cell phones, they decided to let people turn the side tone down, and so you get these shouters all the time. But actually I found that the solution is not to explain what a side tone is to the person, but little 19-cent pieces of foam that you put in your ears. Other things in this block diagram, it shows the hook switch, which we've already discussed. This is a little interrupter kind of switch, and it's connected to the hook. When you pick up the handset, that switch closes, connecting the two wires together. The rotary dial switch was used for address signaling. And the way that this worked in plain ordinary telephone service was you got a telephone, and it had originally a metal dial with holes in it, and it was a plastic dial. And if you wanted to signal a 4 to the switch, you'd put your finger in a little 4 hole, move the dial around and let it go, and as it moved back, there was a spring attached to this little switch inside the telephone that would cause that switch to go click, 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 click 4 times. Now, while you're doing this, you're off hook, so the hook switch is closed, so electricity is going around the loop, and then the dial switch opening would momentarily stop the electricity, then start, stop, start, stop, start, stop. And from the telephone switch's point of view, what we would see is big pulses of electrons, or you could represent that as pulses of voltage on the wires. And so this is referred to as pulse dialing or pulse signaling. Now, what's the difference between the switch attached to the dial and the switch attached to the hook, other than the fact that one of them is normally open and the other one's normally closed? Well, nothing. They either make or break the loop. This is Flintstones era technology we're talking about. Now, knowing that those two switches do the same thing, then you should be able to signal network addresses to the telephone switch using the hook switch on the telephone. Here's your homework assignment. I'll give you the numbers. You have to hold the button down for 45 milliseconds. That's 45 1,000th of a second. And then you have to let it up for 55 milliseconds. That's one pulse. And so if you wanted to signal a 4, you'd have to do that 4 times in a row. Then you have to wait the interdigit interval, which is 7/10 of a second, 700 milliseconds, and then you can do the next digit. So your homework assignment is to attempt to signal 411 to your local telephone company using the hook switch on your phone. And with a bit of practice, it's easy to do. It works out to 10 beats per second, so it's 411. And with a bit of practice, you will succeed. Now, if you do succeed, what do you do next? Well, you say, oh, sorry, dialed the wrong number, and hang up before they charge you $1.50 for directory assistance. If you fool around too much on the line, it may go dead. Don't panic. Just put the phone back and leave the room so nobody knows it was you who did that to the telephone service, and wait about 20 minutes. Your phone will come back to life. There's a protection circuit on the switch in case something goes wrong. It'll cut off the service. Just a couple of other things on this diagram. We've got line voltage going from one wire labeled ring to the other wire labeled tip, and we've got a protection and a ringer across the two wires. Let's just cover those items to finish off our discussion of pots. The two wires, which are the loop, actually have names. One of them is called tip and the other one is called ring. And this comes from a comedy show called Rowan and Martin's Laugh-In. On Rowan and Martin's Laugh-In, there was the character Ernestine, played by Lily Tomlin. Ernestine was a switch. I mean, these were the first types of telephone switches, was people. And Ernestine had this big patch board where there would be jacks in it for all of the loops locally, and then other jacks for trunk circuits going off to the world. And if you wanted to make a phone call, you had to alert Ernestine by maybe jiggling up and down on your phone hook or something like that. And then you would have to say to Ernestine, I want to make a trunk call to Chicago. And Ernestine would take a patch cord and plug your loop into a trunk circuit going to Chicago. This is what switches do. They do it automatically now. The patch cord used by the operator was cleverly designed so that the two wires appeared on a single connector. And the way it worked was on the connector on the patch cord, the tip had one of the wires connected to it. Then there was a bit of insulating material, and then there was another conductive ring on the connector, and the other wire was connected to that. So when it plugged into the jack, it connected the two wires at the same time. So the one connected to the tip of the connector is called tip, the one connected to the ring was called ring. The line voltage is minus 48 volts, and that's minus 48 measured from ring to tip. And what that means is if you took a voltmeter and put the negative probe on ring and the positive probe on tip, the needle would read minus 48 volts. Now, why do we use minus 48 volts instead of, say, plus 48 volts? Well, money once again, but in this case it has to do with deteriorating assets. It turns out if you charge stuff up with a negative voltage, it doesn't rust. If you charge stuff up with a positive voltage, it rusts very quickly. It has to do with something between the charge on oxygen ions and the charge on the earth. More than that, I don't know. You'd have to go look it up in a chemistry textbook. All bridges are charged up with a negative voltage. They don't rust. Parking garages, ships at sea are charged up with a negative voltage. Sometimes it's done by putting a block of zinc on the engine or on the boat, and this acts as a sacrificial anode or something like that. The telephone company charges up their wires with a negative voltage so they don't rust. Other than that, it doesn't make any difference. Unless you were working in the battery room at a central office, you'd probably want to know which one was positive and which one was negative. But other than that, it doesn't really make much difference. When you go off hook, they drop the voltage from minus 48 volts down to about minus 10 volts. Why do they do that? Well, what's another way you could make the phone company think you went off hook? You could take the two wires leading to the telephone, cut them, strip the insulation off that red wire and that green wire, and stick them on your tongue. And then the electrons would come from the line card down one of the wires across your tongue to the other wire and back to the telephone company. Now, 48 volts, that's DC, that's deadly force. You can kill somebody with 48 volts. But 10 volts, well, your skin has enough resistance so that if you touch 10 volts DC, it won't cause electricity to go through your brain or your heart or something bad like that. Let's talk about these last two boxes, protection and ringer. The ringer is for the other half of supervision. How does the switch indicate to the user that it's the switch that wants to start communicating? We put a voltage on the wires, yet another voltage, but this one is quite high voltage. It's 100 volts RMS. What does RMS mean? Average for things that vary. And this voltage is varying 20 times a second. And they apply this voltage to the line for 2 seconds, and then they don't for 4 seconds. 2 seconds on, 4 seconds off. Now, inside the telephone, there's a little circuit sitting across the two wires, which are the loop. When your phone rings, you're on hook, so the hook switch is open, so all that electricity goes through the ringer, and it makes your ringer ring for 2 seconds, and then not for 4 seconds, and it rings for 2 seconds, not for 4 seconds. This is how the switch requests that you start communicating with it. How do you acknowledge that request? You go off hook, closing a little hook switch, and it causes current to flow around. The last thing on this slide is protection. When you're using a telephone, what you're doing is holding the end of a very long lightning rod about 2 inches away from the main processing part of your brain. Sound like a good idea? I mean, those wires, which are the loop, could be literally strung up on poles for 3 miles down the road. And if we get a lightning strike on there, it's going to cause this huge surge of electrons to come down the wires, exit the speaker, go through your brain, back into your mouth, and back to the telephone company. Good idea? So we always need protection circuits across the two wires to protect the user from getting electrocuted during lightning storm. Usually we have a protection circuit on the D mark. That's the little box on the side of your house that demarcates the telephone company's wires from your inside wiring. It's got a little cover and some brass bolts with nuts on that the wires screw onto. But the telephone also has to have a protection circuit in it, just in case the one on the D mark isn't working or isn't connected or isn't grounded properly. The one on the D mark is usually connected to the ground, so we'd send all the extra electrons into the ground. The one on the telephone short circuits when the voltage gets too high and sends them back to the phone company. And then they've got circuits that actually send the extra electrons into the ground at the central office. One problem with POTS is the address signaling mechanism, where we use dial pulsing. There are two problems with that. One, it's pathetically slow. Two, you can only signal to the telephone switch. You can't signal anywhere else. As far as being pathetically slow goes, remember it's hold the button down for 55 milliseconds, up for 45 is one pulse. So it's 1/10 of a second per pulse. Now, for example, a 0, that's not 0 pulses, that's 10 pulses. So to signal a 0, you have to go click, 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 and then wait the interdigit interval. It takes 1.7 seconds to signal a 0. This is ridiculous. So there's an improvement called touch tone. Actually, touch tone is a registered trademark of AT&T. The generic term is DTMF, dual tone multiple frequency. Some mornings I wake up and I think, yeah, that makes perfect sense, dual tone multiple frequency. Other mornings I wake up and I think, well, there has to be a faster way of saying that. In any case, what we do is we have a keypad with buttons on it, and we define tones in a grid pattern. And for example, if you look at this chart, if we wanted to signal a 4 from the telephone to the telephone switch, we'd press the 4 button and it would generate 2 tones at the same time. In this example, one at 1209 Hertz and one at 770 Hertz. So 2 tones out of multiple frequencies, dual tone multiple frequency. Now, why would we generate 2 tones for each button instead of, say, 1 tone per button? Well, it's answer number 1, money. On a traditional telephone keypad, there are 12 buttons. So if we had 1 tone for each button, you'd need 3 times 4 is 12 tones. But if we do it in a grid pattern like this and generate 2 tones for each button, then you need 3 plus 4, which is 7, so it's cheaper. You only need 7 tone generators in the telephone and 7 tone detectors on the line card instead of 12. There are actually 16 buttons defined in the standard, although on most telephones you'd only see 12. The other 4 shown in this diagram, labeled A, B, C, and D, are generally not available on regular telephones. Maybe a technician would have a fancy telephone with 16 buttons on it, but most of the time they're used just for special signaling features like caller ID with call waiting, which allows you to get the caller ID of a second call while you're on the phone. And caller ID is a little modem signal that's transmitted with the phone number of the person who's calling you. But if you're already on the phone, well, we don't want to listen to a modem transmission, so the line card uses one of these special tones to tell the telephone to turn its speaker off, and then it sends the caller ID, and then it uses another tone to tell the telephone to turn its speaker back on again. So it will mute in the listener's ear while we transmit the caller ID of the second person. So they're just used for fancy features like that. Now, besides being faster, you only have to press one of the buttons for 50 milliseconds, regardless of which button it is. The other advantage of DTMF is that it's an in-band signaling system. What we mean by in-band is that we are using the capability set up to do voice communications to also do control information communication. This chart, once again, you'll notice that all of these numbers, these single pure tones, these are all within the voice band of 300 to 3300 Hertz. So what we're doing is using the voice communication capability to signal control information. And the advantage of that is that once you have a voice communication path set up to the far end, we can again use the signaling system to talk to far end equipment, like say a voicemail system, and tell it to delete that message, listen to the next one, and save it by touching touch tones. For setting up phone calls, in other words, communicating the called number all the way along the chain to the far end telephone switch, in the old days we used a technique very similar to DTMF called MF signaling, which was again an in-band signaling technique using tones on the trunk. So we go beep, 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 sending the phone number down the chain to the far end switch. And the specification was it could take up to 30 seconds to set up a phone call to get all the way to the far end just to find out that it was busy. And it's the far end telephone switch is the one that sends the busy signal back. Then a system called SS7 was introduced, and this is an out-of-band signaling system. In other words, there's a separate path for the data and for the actual voice communications. And this is what we use to set up phone calls and communicate information on the public telephone network. If you look at this diagram, the components of the SS7, service control points, computers and databases in centralized locations, connected to telephone switches, which are called service switching points in SS7 lingo, via the message transfer part. In a perfect world called the Advanced Intelligent Network, telephone switches would be completely dumb, and all of the smarts would be in these centralized computers called the SCPs. And the way it would work is that when you dialed a telephone number, your switch would send a message to these centralized computers saying, well, what should I do with this phone call? And the centralized computers would make the routing decision and send an instruction back to your telephone switch saying, well, you're going to use trunk circuit number 100638974 for this phone call. And your switch would say thank you very much and seize that trunk. And then the centralized computers would send a message to the far end telephone switch telling it what the called number was so it could figure out which line card to look at to see whether it was busy or not. And this changed the call setup time down to less than a second. Lowering the maximum call setup time down to less than 1 second means that we don't have to have as many trunks for non-revenue bearing phone calls. Now, telephone companies are reluctant to go the whole way down this road, and this is because of experience after the system was first set up. What's the problem with this? Well, single point of failure. What happens if that service control point crashes? No more telephone calls. Now, of course, they knew about this. It's not some sort of big surprise. And so these SCPs are always duplicated. They're two computers and two databases, and they're always making the same calculations and checking each other. And it's supposed to fail safe. If one computer starts making mistakes, the other's supposed to shut it off. Now, shortly after the system was deployed, some technicians in New Jersey were testing this idea to see if it failed safe or not. And they crashed the entire telephone system on the eastern seaboard for 9 hours. They purposely introduced a bug in one system, and instead of the computer that didn't have the bug shutting off the one that had the bug, the opposite happened, and then the bug spread to all of the other SCPs. Those two people shut down the whole phone system all the way from Maine down to Florida for 9 hours. Where are those people today? We're not sure. Now, because of this, the SS7 is not generally used for normal call setup. Every switch has a little database, which might be called its routing table, and there's yet another overlaid control system that updates those switch-based routing tables every 10 seconds. The idea being that the control system can crash. The switch still has its last copy of the routing table. It tells you how to get to every other exchange. And it can continue to use its latest copy to make phone calls. What SS7 is used for is for fancy services. And an easy example of that for residences is call forwarding. If you pay the $5 a month, then you can pick up your phone and dial *71 or whatever it is, and you hear beep, 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 beep. That's a call progress tone. That means you're now talking to the SCP, probably indirectly. And then you can punch in the number you want your calls forwarded to and hang up. Residential service usually have to do this twice to confirm the number. What you just did was two things. You put a trigger on your line card and an entry in the database in the SCP. The trigger, this is a bit that gets set, means that when the switch is just about to complete a call to your line card, it sees the trigger set, so it doesn't. It does a database lookup on the SCP, and that says, oh no, well, don't complete the call there, reroute the call over to here instead. An example of where this service is used for business customers would be call centers, where, say, for example, an airline has got multiple different call centers across the country, and you dial 1-800-UNITED. Usually it would depend what part of the country you're calling from, whether you went to the call center in Omaha or the call center in Oregon or the call center in Maine. But the idea not only is that it's the same phone number, 1-800-UNITED, everywhere across the country, but it's directed to different places depending on where you're coming from. This is all SS7 stuff. But if they pay extra, the airline can do load balancing between the call centers. And this would mean if, say, for example, the call center in Omaha gets really busy, it can send a message into the telephone system to the SCP saying, stop sending phone calls here, we're busy, send them somewhere else. And then if somebody in the city of Omaha called 1-800-UNITED, they might go to Maine instead of the call center in the same city. And this capability of being able to talk to the telephone system and have on-the-fly rerouting of phone calls, all of this stuff is all SS7 capability. The other thing it's used for is credit authorizations. You want to make a phone call using a calling card, somebody has to do a credit authorization on that calling card before the call's completed. And anytime we're talking about a database lookup and control information back and forth, we're always talking about SS7. This system is used to connect all of the telephone companies together, and it's used to connect all of the wireless companies to all of the wireline companies and connect all the wireless companies together. This is why you can do roaming from one network to another, is because when you try to make a phone call and you're in a foreign service area, a message will get sent over this SS7 network to all of the other companies saying, ever heard of this phone before? And an answer hopefully will come back from one of them saying, yeah, that's one of our customers, give the person a dial tone. So this system is used to connect phone companies together, and it's used to support fancy high-end services. It's not used in most telephone companies for just regular POTS phone calls. That's switch-based routing. Now we're going to pick up the pace a bit and talk about some of the equipment that can be connected onto the public switch telephone network. And the most important type of telephone equipment is a switch. This graphic shows a photograph of a telephone switch. This is a DMS100 telephone switch in a big central office. Looking at this picture, you can see the front row of racks of equipment. And it's got the controller and the processors and the hard drives and the user interface and things like that. Now this is just the first row. There are rows and rows and rows of racks behind that full of line cards that we discussed in the previous chapter. Looking at a photograph of a telephone switch doesn't give me a good idea as to what it does. I mean, it's just a big rack mount computer system. This graphic gives me a much better idea of what a switch does. This is an aerial photograph of a railroad switching yard. And if we stop and think, well, what's a switch in a railroad yard? Well, it's a lever that you move like this, or something you turn like that, and it makes the tracks go like this. So what we've done is we've implemented a routing decision to connect one spur line to a main trunk line going off, and a whole bunch of stuff can go that way, but then we might change the routing decision later on. And this is what telephone switches do. They connect a loop to a trunk for the duration of a communication session. And a whole bunch of stuff is going to follow along that trunk, but then we might change the decision and connect a different loop to the same trunk for a later communication session. Telephone switches connect loops to trunks. They also connect loops to loops for local phone calls, and deeper into the network there are switches that connect trunk to trunk for long distance phone calls. Now, telephone switches are computers. Residential loops are copper wires, and they're terminated on line card modules, and there are rows and rows and rows of racks and racks and racks with drawers with big pieces of fiberglass with lots of line card modules plugged onto them. That's mostly what a telephone switch is. As we're going to see as we get deeper into this story, the trunks are all carried on digital carrier systems, which most of the time are implemented using fiber optics. So the trunks would actually appear on fibers terminated on fiber line cards in this computer we're calling a telephone switch. In the next chapter, we're going to see that what we have to do to actually implement this connection is to transfer a byte from one input on this computer called a telephone switch to another one 8,000 times per second. 1 byte 8,000 times per second. Is that an onerous task for a computer to transfer a byte 8,000 times a second? Well, let's think about the 286 machine. This was the IBM PC-AT, Advanced Technology. I bought one of those for $3,400. The great thing about the PC-AT was it had a 16-bit wide bus inside the computer. So it could move 2 bytes at a time on the internal bus. This was a big improvement because the PC was an 8-bit bus. It could only move 1 byte at a time. And on the PC-AT, it could move 2 bytes at a time, and it could do this 8 million times per second. So it could move 2 bytes 8 million times a second. In order to do a phone call, you have to move 1 byte 8,000 times per second. So if you didn't count the overhead, which you would have to, on a 286 machine, you could do 2,000 simultaneous phone calls. So no, moving phone calls around is not an onerous task for a computer. It's trivial. The processor in a DMS 100 is less powerful than the processor in my laptop computer. Just moving the phone calls around is easy to do. It's all of the fancy features like call forwarding and ring again and camp on and all the SS7 database lookups. These are the things that load the processor on a computer. If you have a lot of telephones inside a building, you can get your own telephone switch. You don't have to use the telephone company's telephone switch. Now, when you get your own, this is called having a PBX. It stands for Private Branch Exchange. Exchange is another word for a switch, and this is a private switch. You've got your own in your building. Why is it called a branch exchange? As you can see on the graphic, all of the telephones inside the building are connected to the PBX. The PBX is then connected to the nearest central office. Now remember, things that connect switches together are called trunks, but these are a special type of trunk called PBX trunks. And the central office, of course, is where the main trunking system terminates. So the reason why this is called a private branch exchange is that this is a private switch on a branch off of the main trunking system. Trunks, branches, I'm not making this up. With the PBX, you provide your own services locally, including switching, and you can do things like 4-digit dialing between cubicles inside the office. Now you can get all of the same stuff from the telephone company. From the telephone company, it's called Centrex. And there are 3 main differences between Centrex and PBX, and these are location, location, and location. It depends whether the telephone switch is in your telephone room or whether it's in the central office. Other than that, they're pretty much the same thing. If you get service from the telephone company, Centrex, they will take your telephones, they have 600 phones inside your building, and they will connect them all to the central office switch, the same one that's providing residential service in that area perhaps, but they'll run a little software program on the CO switch called a Centrex partition, which makes it look like you have your own little switch. Now, if you have 600 telephones in your office, they're not going to run 600 telephone lines down the street to your office building. They're going to run a loop carrier system, probably on fiber optics, which will terminate on a loop carrier system terminal in the telephone room of your building. And from there, we've got connections to all of the telephones. So from a topology point of view, it ends up looking very similar. It really depends whether the telephone switch is sitting in your telephone room or in the central office. Now, why would you go to all the trouble of getting your own telephone switch? Well, answer number one, money as usual. One of the main differences between PBX and Centrex is that the pricing model is different. With Centrex, you pay for everything on a per line basis, so you pay a monthly charge per line, but then all of the value-added features are also per line. For example, if you want to get voicemail or call forwarding, that would all be per line. How do you get voicemail or call forwarding on a PBX? Well, those are just software features that you run on the PBX. And also another reason why it's cheaper is with Centrex, you would have 600 connections to the telephone company. With PBX, you don't have one PBX trunk for every telephone connected onto the PBX. No. There's usually about a 10-to-1 ratio. So if you had 600 telephones connected onto the PBX, you might have 60 trunks going off to the telephone company. And so you're only buying 60 connections to the telephone company instead of 600. Now, of course, PBX trunks are more expensive than individual lines. From a technical point of view, they're exactly the same thing, but don't tell anybody. They change the name so that they can jack the price up. But still, it's going to be cheaper to pay for 60 connections than 600. Another reason why PBX is cheaper is because of moves and changes. If somebody changes cubicles in an office building and they want to keep the same telephone number, a technician has to sit down at the switch and tell it, do not associate that 4-digit extension number with this pair of wires anymore, associate it with that pair of wires now. If you've got a PBX, you can hire somebody at minimum wage to do this programming of the computer every time somebody changes cubicles. However, if you've got Centrex service, you don't have access to the telephone company switch in the central office to reprogram it. You have to pay the phone company to do that. How much does that cost? Well, $80 anyway, maybe more. And how often do people change cubicles in your organization? Well, at least once a year. So right there, we've got $100 a year per line hidden cost for moves and changes with Centrex that you can do yourself with PBX. This issue may go away to some extent, not completely, but to some extent with voice over IP, and we would certainly discuss that in the voice over IP series of courses. But for traditional switches, this is a big issue, $100 a year per line. Now, of course, just like everything else, this has its upside and its downside. The upside is you can save money by doing things yourself and providing services yourself. What's the downside? Well, you're going into the local telephone business. So you have to have a room to put the telephone switch in. It has to have heating and air conditioning. Your insurance company will probably make you buy a halon fire suppression system for that room. You've got to have physical access control. You have to have technicians that know how to run the PBX. And you have to power the PBX. Now, most of the time, it's the telephone switch that powers the telephones. And so when we're talking about powering a telephone switch, we want to have an uninterruptible power supply so that the phone system keeps working if the local electricity company goes on vacation. How do you get an uninterruptible power supply? Well, the way that it's done is that we've got the line card on the switch is putting voltage across the two wires. We put batteries across those wires. They're sitting there all the time, but most of the time there's a power system that takes the local electricity company's power and converts it to the minus 48 volts and puts it onto the loop. The whole idea with an uninterruptible power system is that if the electricity company goes on vacation, the batteries are still sitting there connected and can continue to provide uninterrupted 48 volts on those loops. Now the question becomes, well, how long do you want the telephone switch to keep working after the power shuts off? And if the answer is 0 seconds, that's fine, as long as all of the officers of the company sign their names to an agreement saying, we agree that when the electricity shuts off, so does the telephone system. That's fine. But they might say, well, let's have the phone system run for 5 minutes after the electricity shuts off. How do you get a 5-minute UPS? Well, remember, most telephone switches run on 48 volts, minus 48 volts. And car batteries are 12 volts. So in theory, you could go to Sears and buy 4 diehards and connect them together in series. 4 times 12 is 48. And then you take the positive terminal and plug it into the ground. And then you've got minus 48 volts in your hand on the negative terminal. You could run a telephone switch for a few minutes with that. If you want it to run for more than a few minutes, you got to have a generator to keep those batteries charged up. And in small locations and remote locations, we use propane as the fuel because it's easy to handle and it doesn't degrade. In big installations, of course, we use diesel generators. Now, diesel generators do not maintain themselves. Somebody has to start the thing every month. And we have to have a fuel supply for the generator. Now, maybe the requirement is, no, our company, this location, it has to keep running. This is one of our main call centers. The phone system isn't allowed to go down. Now, let's say that the big quake has struck, or the big tornado has struck, or the big hurricane has struck, and all of the power in a 50-mile radius around the building is on the ground, and it's not going to be coming back up anytime soon. What that means is that you have to have a guaranteed delivery of fuel for your diesel generator. When everybody's clamoring for fuel and the National Guard is protecting the fuel convoys, they stop in front of your building and not somebody else's building and deliver fuel. You can figure this all out. You have to sign that contract before the disaster happens, not after. And you can certainly do this all yourself, and companies like Boeing certainly do this. It often comes down to a question of what business are you in? If you're a huge company and you've got a telecom department and you've got the energy to hire people to do all this stuff, that's fine. But if you're some small .com startup, you don't want to spend your energy going into the phone business. You're going to pay the phone company to do this for you. That's called Centrex service. Now, Centrex service is not a money-losing business at the phone company. It's a money-making business. It's part of their bread and butter. But it comes down to a question of, do we want to do it ourselves and save some money? Or do we want to concentrate our energies on our core business and pay the phone company to do the phone service, knowing that they make a bit of money on that? Some of the other issues to keep in mind when you're considering PBX versus Centrex, one of them is maintenance and scalability, and these two things are tied together. Let's say you're starting some company called, say, for example, Microsoft, and you've got 20 employees, so you buy a PBX that can be scaled up to a maximum of 10,000 lines. You've only got 20 employees, that should be lots. Well, what happens when you hire employee number 10,001? You have to do a forklift change. What's a forklift change? Well, that's when you go into the telephone room with a forklift and you pick up the 10,000 line PBX and drop it off the edge of the loading dock and then put the shiny new 100,000 line PBX in its place. Upgrades, if we want to go to voice over IP and you've already invested $1 million in that PBX, can it be upgraded, or do you have to throw the thing away and buy a whole new one to change over to voice over IP? These questions are ones that you would want to consider, and you can pay the phone company to take care of all of that stuff, or again, you can do it yourself. Now, from a budgeting point of view, there's another point, and this is a real one, where we see organizations coming to telephone companies saying, well, we went down the PBX road, but the problem is that the costs weren't predictable. We kept having big spikes in the maintenance costs from one month to another, and that doesn't work. We kept blowing our budget, and I'm getting in trouble. I need a contract where we have somebody who's going to maintain the PBX for us at a fixed monthly cost. And so telephone companies like Cincinnati Bell, for example, part of their business is as a service maintaining organizations' PBXs for them. And you can be sure that once they've signed the contract, once the network people at Cincinnati Bell say, well, okay, we have to maintain this Hitachi PBX, why don't we just throw the thing away and connect all these customers to our CO switch? It would be a lot cheaper for us to give them service that way rather than maintaining their PBX for them. The last topic here is direct inward dial. You thought you were going to save money getting a PBX? Well, the telephone company's been in business for a long time, and they've had a lot of clever people thinking about this for a long time. What about network addresses? How do you get telephone numbers for your telephones when you connect them to a PBX? Well, it turns out that you have to rent them from the telephone company, and they got a big block of them for free while the getting was good, and they rent them out for $7, $8 a month each. The question here is, how do we get this telephone to ring if you call it from a payphone? There are 3 ways of doing that. One is called having an attendant. Second is called having an automated attendant. And third is direct inward dial. Having an attendant, this is a person, an operator, means that you get 60 trunks from the telephone company, but they all have the same telephone number. It's 765-2000. And whenever anybody calls in on one of those trunks, the call always goes first to the attendant console, and that person answers the phone and says, "Welcome to ABC Company, who do you want to talk to?" And using your voice, you tell the attendant, "I want to talk to Mr. Smith." So they look it up and they see what Mr. Smith's extension number is, and the attendant types the extension number into the attendant console and presses transfer. So the attendant programs the PBX and tells it which loop to connect that trunk to, and then start that loop ringing. That's called having an attendant. Now, of course, people are expensive, so the next step is to get rid of the person and replace it with a computer, which is called an automated attendant or an interactive voice response system. And this is where you call a company and a computer answers the phone and says, "Welcome to ABC Company. If you know the extension number of the person you want, punch it in now. Or if you want technical support, press 1. If you want customer service, press 2. If you want the black hole, press 6. Now, if you just want to connect to a particular person and you know their extension number, well, what you're going to use is use your DTMF tones in band signaling to talk from your telephone to this automated attendant or IVR and tell it the extension number of the person you want to talk to. So you program the PBX by punching in buttons, and then it connects that trunk to that loop and starts the loop ringing. Some organizations don't like the idea that you have to go through an intermediary in order to get to your final destination, like to the sales department or to your salesperson, because maybe you're going to hang up. They want to have it so that you can call directly and make that person's phone ring without going through an intermediary, and that's called direct inward dial. The picture looks exactly the same, except that every one of the telephones connected to the PBX has a public switched telephone network address associated with it. And so instead of having one number for the whole company, like 765-2000, if you dial 765-2010, then that's going to make this phone ring. If you dial 2011, that's going to make that phone ring. If you dial 765-2012, that's going to make this phone ring. Now what's going on here? The picture's the same, the hardware's all the same. Well, it turns out that you, as a caller, told the telephone company which extension number you wanted, right? You dialed 765-2012. You told the phone company, I want extension number 2012 at that company. And then what they do is their CO switch tells the PBX there's an incoming phone call in this trunk. Do you want to accept it? And the PBX says yes, and then the CO switch says, by the way, this call is for extension 2012, and the PBX says thank you very much and automatically connects it to that loop. So you can tell a person, and a person programs the PBX. That's called having an attendant. You can tell a computer, and the computer programs the PBX. That's called having an automated attendant or an IVR. Or you can tell the phone company, and the phone company programs the PBX. That's called direct inward dial, and the last option costs $7-8 a month per line. If you go down the PBX road and you have a large company, you may well end up getting one PBX at each of your large locations. The phone company, of course, that has services to sell you, and one of them is called a VPN. Now you have to be very careful with the term VPN because it's used in the PBX's business to mean one thing. It's used in IP to mean something completely different. In the IP world, a VPN is secure communications across an IP network using a set of protocols called IPsec. And we will certainly talk about those in an upcoming discussion. Here we're talking about something completely different, even though it uses the same three letters, VPN. In the PBX voice business, a VPN is two things put together. It's abbreviated dialing and watts. Abbreviated dialing is when you can pick up a phone in Chicago and press 4 buttons and a phone in Los Angeles rings. You only pressed 4 buttons. What's going on there? Well, obviously a computer looked up what the routing to that extension number was and dialed it for you. This is called abbreviated dialing. It's just a database lookup service. Watts, that stands for volume discounts, but we couldn't call it VD service for obvious reasons, so we had to think of another name. It's called wide area telephone service. All it is volume discounts for phone calls. Now those two things together, abbreviated dialing with volume discounts, that's called a VPN service. But you have to be very careful about that term because most of the time when somebody says VPN these days, they're talking about IPsec. They're talking about secure communications across an IP network that has nothing to do with this use of the three-letter abbreviation VPN. To finish off, we'll just go through some of the other equipment, particularly that's used in a call center. This graphic shows a block diagram of the equipment that goes into a call center. We've got a switch, and typically that's a PBX. We've got an interactive voice response system, an IVR. We've got an ACD, an automated call distributor. There's a customer care system. This is the big database system running on IBM mainframe or Oracle or Unix or something like that, where all of the records for the customers are stored. And we've got agents who can access customer records, modify them, and talk to the callers, the customers, over the telephone. IVR stands for Interactive Voice Response System. And these are the boxes we love to hate that say for sales press 1, for technical support press 2. The purpose of the IVR is to determine two things. One, who the customer is, and 2, what they want to do. Now, ironically, we cannot use caller ID to ID a caller because it doesn't. It IDs what pair of wires they're calling from. It doesn't say which person is calling. So a lot of the time when you call up and you get intercepted by an IVR, say for example you phone an airline, what they're going to say right at the beginning of the script that you're going through is say, please punch in your frequent flyer number, because then we know who you are. Then they might ask you to make a selection out of a menu. If you want to make a change to an existing reservation, press 1. If you want to make a new reservation, press 2. If you want to complain, press 6. At this point, we found out who the person is and what they want to do. So we would stop sending the call to the IVR and we would send it to the ACD instead. ACD stands for Automated Call Distributor. And this is a computer where we can set up queues where people wait, and then we can assign agents to the queues. And the queues can have different priorities, and they can have different groups of agents serving them. For example, at the airline, we would set up one queue for people who have flown more than 1 million miles with us. We'd set up another queue for people who have flown 100,000 miles. We'd set up a third queue for people who are in our frequent flyer program, and then a fourth queue for people we've never heard of before. And this system then plays music on hold and treats you not to hang up, and some of the sophisticated ones will tell you how long it's going to be on average until your call's answered. The whole idea with this is that when the ACD finally finds an agent that's able to answer your call, what it's going to do is switch the phone call down to that agent. Now, in an integrated call center, it's going to do something else, because we know who you are and we might know what you want to do. In an integrated call center, the ACD, at the same time that it causes the telephone call to be switched down to the agent, it's also going to pop a message to the customer care system and will cause your customer profile to pop up on the agent screen. So we get a simultaneous screen pop and phone ring at the agent. And this saves a few seconds, and so in the long run it means that the company doesn't have to hire as many agents. This story is getting dispersed. Originally, it was a customer premise-based solution where all of this stuff would be in one big building. There'd be a huge beehive of cubicles of people answering the phone, and if they wanted to go to the bathroom, they'd have to hold a paddle up to ask permission, and sometimes they weren't allowed to go to the bathroom because the call center wasn't meeting its call answer targets, and then other times they might be allowed to go to the bathroom, but it would be timed how long they were away from their desk for. And the company would buy an IVR, and they would buy an ACD, and they would maintain this and set it all up themselves. Well, we've started outsourcing this stuff. First, of course, the PBX can be outsourced. That's pretty easy to do. Lots of companies will provide that service. We've been outsourcing mainframe services forever. The things that are starting to get outsourced now more and more are the IVR ACD functions and the agents. There's quite a business in companies setting up all of this hardware, the IVR and the ACD, and saying to one of their customers, well, look, you don't have to go to all the trouble of figuring out what IVR to buy and which ACD and how to configure them and maintain them and set them up. We'll do all that stuff for you. You just send us what menus you want on your IVR and what queues you want on the ACD and what phone numbers to associate them with, and we'll provide that all as a network service to you. That's quite a big business. And of course, we've started moving the agents to places where labor costs are cheaper. We all have probably run into having a phone call answered by somebody in India when you call, for example, Dell and Microsoft. Both of them have call centers in India. Now, from my point of view, I don't really care where the person lives or what language their mother spoke to them or what color their skin is. It's can they answer my question? And my experience has been is that you get the same level of morons. It doesn't matter whether they're based in North America or based in India. In this chapter, we're going to take a look at the telecommunications industry and understand the different players and how they fit into the picture. We'll start with AT&T, which of course provided local and long-distance service across most of the United States for the better part of 100 years. AT&T in the 1980s was broken up to settle a U.S. Department of Justice antitrust lawsuit. And the way that AT&T was broken up was that the continental United States was divided up into 195 geographic areas called LATAs. And a LATA is a local access and transport area everywhere except in South Boston. What's a LATA in South Boston? Well, that's a thing that you lean onto the side of your house to get up onto the roof. But everywhere else, a LATA is a local access and transport area. It's a physical geographic area. And the piece of AT&T, or the Bell System's local operations that found itself inside one of these LATAs, became a telephone company, a LEC, a local exchange carrier. The ownership of these LECs was then spun off or divested to 7 holding companies called the Baby Bells. And we had US West, Pac Bell, Southwestern Bell, Bell South, Bell Atlantic, NYNEX, and Ameritech. And for example, Ameritech was a big holding company that now owned some LECs that make up the former Michigan Bell. But it's not like they changed anything physical. They just spray painted Ameritech on the side of all the Michigan Bell trucks one night. What was left over after this divestiture of the local operations was the long lines. And that's what AT&T Corp was the day after this divestiture. Now the idea was, if you made a phone call that stayed within a LATA boundary, then the local exchange carrier had the exclusive right to provide access for and to transport that phone call inside the LATA. However, if you made a phone call from one LATA to another, even if the dividing line was down the middle of your street, you had to get 3 companies involved. Local exchange carrier for access, inter-exchange carrier for long distance, and then local exchange carrier for access on the other end. And the way it worked, of course, is that the customer signed a contract with the inter-exchange carrier, the long-distance company, and paid them for long distance. But the long-distance company doesn't have any physical wires going to the customer's home. They had to pay the LEC a per-minute access charge to use the last few miles of wires to actually get to the customer. So this is how the local companies were still subsidized by long-distance operations, was a per-minute access charge. Part of the whole idea here was to implement long-distance competition. And we had MCI, Metropolitan Communications Incorporated of Chicago, and there was WorldCom and XL and a long list of other inter-exchange carriers like WillTel and Alltel. Then some consolidation started to happen. One of the first things that happened was Bell Atlantic bought NYNEX, and they spray painted Bell Atlantic on the side of all of the NYNEX trucks. Another thing that happened was a company called SBC Communications from Texas. First they bought Southwestern Bell, then they bought Pac Bell, then they bought Ameritech, and that reconstituted a large part of the Bell system. When we're discussing this story, sometimes we forget that the Bell system and AT&T was not the whole story. In fact, in 1970, there were 1,600 telephone companies in the United States. And some of them belonged to the Bell system and were owned by AT&T, but most of them weren't. And the ones that weren't were called independents. and there are lots of little independents in small towns in Minnesota, North Dakota. A company called GTE owned a lot of these independents. Remember GTE Sylvania light bulbs? Well, they sold off their Sylvania light bulbs division and concentrated on owning phone companies for a while. The next consolidation in the telecom business that happened was that Bell Atlantic and GTE merged together, and they changed their name to Verizon. Verizon is a focus group name. It's a combination of veritas, the Latin word for truth, and horizon. So we will lead you to the true horizon. Now the story didn't stop there. As things progressed, the value of being a pure inter-exchange carrier dropped. And if you looked at AT&T Corp, this is the long distance company, you looked at their quarterly revenues, they went pop, 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 and they were just on a straight downward slide because we were moving to flat rate and even free long distance. So the latest thing that's happened is that the companies that were inter-exchange carriers, AT&T Corp and MCI, realized that they didn't really have a viable business just selling long distance anymore and put themselves up for sale. And what happened was that SBC purchased AT&T Corp and MCI was purchased by Verizon. SBC then adopted the AT&T brand, of course, it's a very valuable brand name. Pac Bell, Southwestern Bell, Ameritech, and some other things they'd purchased, plus AT&T Corp, the long lines, that was then all referred to as the new AT&T. Then AT&T announced the purchase of Bell South. This was not a big surprise, as AT&T and Bell South had already integrated their wireless operations into a company called Singular. Going forward, Bell South will be called AT&T, and Singular will be AT&T Wireless. Verizon, when they bought MCI, didn't really want to use the MCI name because of that long tragic story with WorldCom, one assumes. MCI is called, at present, Verizon Business. So what we have after 25 odd years of grief and turmoil is that the Bell system has been reconstituted into two main pieces, AT&T and Verizon. Some of the other pieces of the Bell system saw different fates. US West was purchased by Quest, which was a company that was putting fiber optic backbones in place, just like Teleglobe and Global Crossing and 360 Networks and Williams and Metronet and all those companies that were trying to put fiber in the ground and then sell capacity on it. All of them went bankrupt except for Quest, and probably because Quest had purchased a piece of the Bell system and had these people giving them monthly phone bill money every month to keep them out of the bankruptcy court. When we look at maps of the United States to see where US West and Pac Bell and Southwestern Bell were and so forth, and then talk about the consolidation into SBC/AT&T and Verizon, we have these nice large chunks, and it looks like the country was nicely divided up. The truth is a little bit less clear. Here's one graphic that shows in red on the slide the areas that are Verizon service areas. And you can see it is concentrated a lot in New England, but you also see that there's Washington State and parts of California and big parts of Texas are also colored in red there. And that's through the acquisition of GTE. Then if we change to the SBC/AT&T local service areas, then we see that, yes, it is concentrated in the Midwest through Ameritech and in Texas and Oklahoma with Southwestern Bell and some of the big populated areas in California through Pac Bell, plus the most recent addition, Bell South, covering large parts of the southeast part of the country, And they also control Connecticut, if you notice in the top right, through an acquisition of SNET. And when we overlay the two, you can see the areas that these two big service providers, AT&T and Verizon, cover geographically. What are all the blank spots in the middle? These are independents, companies that are not, at least yet, owned by one of the two. For example, Rochester Tel in Rochester, New York. They got 1 million customers, but that's not AT&T or Verizon. They're owned by other companies, I think most recently Citizens Communication. Here we'll cover the Canadian story. For those of you who aren't interested, you just press the skip button on your remote and it will go to the next slide. In Canada, things were divided up along provincial boundaries historically. So we had BC Tel in British Columbia. There was AGT, Alberta Government Telephones in Alberta, SaskTel in Saskatchewan, and they've got MTS in Manitoba. Does anybody know what MTS stands for in the French language? Des maladies transmissibles sexuellement, sexually transmitted disease. Now it's very strange because you go to like Winnipeg and you're walking down the street and they've got MTS written on everything, sexually transmitted disease. And there's a big francophone population in Manitoba, so they know about this. And they had a chance to change it because they privatized the company. It used to be a government-owned company called Manitoba Telephone System. And they could have called it Manitoba Tel or something when they privatized it. But no, they changed the name to Manitoba Telecommunication Services, keeping the MTS. Strange things going on in Manitoba. Bell Canada covers Ontario and Quebec. And of course it's divided into Ontario region and Quebec region. And then there were 4 telephone companies in the Maritimes. There was NBTel in New Brunswick, Maritime Tel in Nova Scotia, Maritime Telephone and Telegraph, Island Tel in PEI, and Newfoundland Telephone. These more or less provincially organized telephone companies were members of an association called Stentor Canadian Network Management. And this used to be called the Telephone Association of Canada way back in 1921. And what Stentor was an association of these big phone companies. They had national brand names, sometimes national billing systems, and most importantly, settlements. Because if you want to make a phone call from, for example, Montreal to Vancouver, that would go over Bell Canada long distance up until the Ontario-Manitoba border. Then they would have MTS for a while, and then it would go over SaskTel, AGT, and finally BC Tel. So each of these companies is carrying the phone call over their network. And if we're charging the customer 15 cents a minute for this phone call, who gets what piece of that phone call? Well, we have to do rate splitting and settlements, and that was one of the main purposes of Stentor. Again, a consolidation happened. BC Tel, AGT, and EdTel merged together to form TELUS Corporation. I've always liked the name TELUS. Great name for a phone company. The 4 maritime companies merged together to form Alliant, and Bell Canada owns a controlling interest. Bell Canada used to own 20% of MTS, but MTS purchased Bell Canada's big competitor for long distance, and so Bell Canada divested themselves of MTS. Both Bell Canada and TELUS are attempting expansions into each other's territory. They certainly have done that through wireless communications, but they're also trying to do it through wired communications, mostly concentrating on business customers at this point. As far as long distance in Canada goes, Stentor was the main story, and today it's mostly TELUS or Bell Canada, and they still do have operating agreements to be able to make a phone call from Montreal to Fort St. John, for example. Bell Canada does have fiber going from the east and terminating in Vancouver, but they need to have operating agreements to go anywhere else in the western part of Canada. Similarly with TELUS. The other main competitor, which today is called MTS Allstream, can trace its roots back to the telegraph companies. Telegraphs were the command and control system for railways. Every railway had a telegraph line running beside it. And after the First World War, most of the railways in Canada went bankrupt, and the federal government merged them together to form the Canadian National Railway System. And there was one main competitor left over, which was the Canadian Pacific Railway. So we had CN Rail and CP Rail. We had CN Railway Telegraphs and CP Railway Telegraphs. The telegraph networks of these two companies were eventually merged together to form CN-CP Telecommunications. Well, at least that's what they called it at CN. At CP, they called it CPCN Telecommunications, and they had two sets of letterhead, one for the office where if you worked at CN, it said CNCP. If you worked at CP, it said CPCN. Anyway, they provided telegraph service across the country. In 1992, they started a joint venture with Rogers Communications, Rogers Cable Systems of Toronto, called Unitel, and this was to provide both business and residential long distance. Now, Unitel started losing money right from the bat, and by some accounts they lost $1 million a day, day after day, month after month. At one point they sold 20% of the company to AT&T Corp in the US and changed the Canadian name of Unitel to AT&T Canada. But it kept losing money, and finally Rogers walked away and said, no, not another cent. And at that point, the banks took over ownership of Unitel, which was now called AT&T Canada. Now, under bankruptcy laws, the banks can't keep goods that they get like that. They have to divest them. And so they were looking for a buyer, and they sold it to AT&T Corp. So at one point, AT&T Canada was 100% owned by AT&T Corp in the United States, which is illegal under Canadian law. The maximum foreign content allowed is 20%. Presumably, the bank said to the federal government, well, either we're selling it to them or we're closing it, take your choice. Subsequently, there were offers to purchase this. AGT looked at buying this company, and that was the breaking point between Bell Canada and AGT, because they were in a coalition and AGT was now looking at competing with them. So that was the last straw that ended up forming this TELUS Bell Canada split. But AGT didn't like the terms that AT&T Corp in the US were offering, so they walked away from the deal. Eventually, AT&T Canada went bankrupt, and they burnt all their creditors and shareholders and re-emerged as Allstream. And then MTS purchased them, and they're now known as MTS Allstream, and they're attempting to provide national communications as a competitor to the phone companies Bell Canada and TELUS. The same regulatory change in 1992 that allowed Unitel to happen, it's called CRTC Decision Number 9212, also allowed resellers to happen. And the idea with resellers is that they can lease high-capacity services from a facilities-based carrier like Bell Canada, and then they can resell them to individuals. And the idea, of course, is that they're buying wholesale and selling retail. But with the shrinking cost of long-distance services, the margins between retail and wholesale dropped to the point where it wasn't a viable business, and every single one of them went bankrupt. Pretty much now all of the former reseller companies like Phonarola, Lytel, Optinet, Sprint Canada, CallNet, they're all grouped under a company called CallNet that's operating under the Sprint Canada name, and Rogers Communications purchased that in late 2005. We've discussed loops a fair amount. Now I'd like to discuss trunks. The idea here is to connect central offices together. Now we couldn't build a fully meshed network. Fully meshed means that everything is directly hardwired to everything else. Why couldn't we build a fully meshed network? Well, answer number one, money. It would cost too much. Just as an example, if you had 25 locations and you wanted to build a fully meshed network, how many circuits would you need? This was senior year high school mathematics. Well, it wasn't the P, it was the C. It turns out that the answer is 25 times 24 divided by 2, which is 300. So to build a fully meshed network with 25 locations, you need 300 circuits. And you start thinking about how many central offices there are in North America. This is not possible. No, we had to put some structure into the discussion. And the basic idea is that each city would have one building called a toll center. And all of the central offices in that city would all home up to the toll center. And the toll center was the jumping off point for doing interurban communications or toll communications. So for example, if you lived in Sacramento and you wanted to call somebody who lived next door to you, chances are very good that they would be connected onto the same switch in the same CO, and so the phone call would go up to the central office over your loop and it would get switched onto their loop. If you wanted to call somebody in Sacramento but they lived 11 miles away, chances are pretty good that they're not connected onto the same central office, so you go up to your central office across an inter-office trunk to their central office and back down. If you wanted to call somebody in San Jose, the chances that your central office have a direct connection to their central office in San Jose are pretty slim. What most likely would happen is that you would go over your loop up to your central office and then up to the toll center for Sacramento and then across an inter-toll trunk to the toll center for San Jose and then back down to the right central office in San Jose and then down to the right telephone in San Jose. Now, because there are so many toll centers, so many cities, we couldn't just build a fully meshed network connecting all the toll centers together. There's more hierarchy in the story. Every state has a primary center where all of the toll centers in that state are home to. The Bell system was always divided into 7 pieces. I mean, this business of 7 baby bells was not a random number. They'd always been divided up that way. So there was a sectional center, and all of the states in that section of the country were all homed up to a sectional center. And if you wanted to go from one section of the country to another, you'd have to go through a regional center. So for example, if you wanted to make a phone call from San Jose to Manhattan, you'd pick up your phone in San Jose, you'd get a dial tone from the central office in San Jose, and you dial 1212 something to make a phone call to New York City. You would go up to the toll center for San Jose, then you'd go up to the primary center for the state of California, up to the sectional center for the Pacific Southwest part of the country, through a regional center to the sectional center for New England, down to the primary center for the state of New York, down to the toll center for the island of Manhattan, and then down to the right central office in Manhattan, and then down to the right telephone. And you can start to see why the SS7 network for signaling was such a great idea, because in the old days, to set up that phone call, we used tones to signal the called number through all of these switches all the way to the far end, just to be able to find out whether it was busy or not. Now we use data circuits and send messages at the same time to all the switches. Since this is a 5-level hierarchy and we started numbering at the top, the bottom level, which is the central office, is called a Class 5 switching office. And so a switch that lives inside a central office is called a Class 5 switch. A toll center is a Class 4 switching office. So toll switches were sometimes called Class 4 switches, are also called tandem switches. That has nothing to do with the company called Tandem, it's the physical arrangement. If we have one thing to which a whole bunch of central offices are homed here, and then another one to which a whole bunch of central offices are homed here, and you go across between the middle, that's called a tandem arrangement in a network hierarchy. One last point here, this 5-level hierarchy of switching centers is notionally correct. In practice, however, the telephone company is going to put in connections between buildings wherever it's most cost effective to do so. If it turned out, for example, that there were a lot of phone calls always going from a particular central office in Sacramento to a bunch of different central offices in San Jose, they might put a short circuit in going from that CO in Sacramento to the toll center in San Jose. So we start getting more of a meshed network. The connections between the switching centers are put in place wherever it's most cost effective to do so. Here we're discussing competitive long distance. The idea with breaking up the Bell system was that the local exchange carrier owns the central office and the wires going to the customer premise. The toll center is the jumping off point for interurban communications. So this is where competitive long distance networks are plugged in, is at the toll center. The place where a competitive long distance company physically connects onto the toll center was called a point of presence, a POP. This is a historical term. When this story first started, all of the people who worked in the toll center would have been Bell System employees. And then under court orders, they would be forced to rent a room in the toll center to MCI. And MCI employees would be allowed to come into the building under heavy security escort and put equipment in this room and connect it on one side to the Bell System's toll switches and on the other side to their fiber optic cables going off to the world so that they could siphon off long distance phone calls and send them over their physical long distance network instead of the Bell System or AT&T Corp. Everybody who worked in the building would refer to that room where the equipment was kept as the MCI room. It was MCI's physical point of presence in the toll center. Point of presence doesn't have to be physically located in the toll center. It could be in a building across the street with a big fiber optic cable running into the toll center. They just have to be able to plug onto the toll switches, which are operated by the local exchange carrier in order to siphon off long-distance phone calls. With a situation like this, if you pick up your phone and you dial 1212 to make a phone call to New York City, which of these long-distance networks are you going to use? Well, it's whichever one you selected. We have equal access, which means that your choice of long-distance carrier is pre-selected and recorded in a database called the PIC database, the Preferred Inter-Exchange Carrier database. And each inter-exchange carrier has a code, so their PIC code is stored against your local phone number. So when you dial 1212, the LEC has to do a lookup in this PIC database to see who your preferred long-distance carrier is, and then it will automatically route the phone call to that physical network. When you change long-distance companies, what really is being done is that the new long-distance company sends a change request to the local exchange carrier asking the LEC to change your PIC code to them. Now, when this was first invented, there were no authentication or security measures on the change requests, and so unscrupulous long-distance companies could change people all over to their inter-exchange carrier service, unbeknownst to the customer. And there was even a buzzword invented for this called slamming. Presumably today there is some authentication on when you change who your long-distance carrier is. If you go to an airport, which long-distance carrier are you going to use to make a phone call? Well, whoever the preferred inter-exchange carrier of the company that owns that payphone is. And there's an interesting scenario here. We deregulated payphones and long distance. So if you pick up a payphone and you dial 1212, now you haven't said how you're going to pay for that yet. The phone call's not going to get completed. It's going to go to a billing system that the payphone company is using. And let's say that's Eric's Fly-By-Night payphone company, and we've hired Eric's Fly-By-Night reseller services and Eric's Fly-By-Night operator services to do all of the connections. So what's going to happen when you pick up the phone and dial 1212 from New York City? My brother is going to come on the line and he's going to say, Pacific Telecommunications Corporation operator, how would you like to pay for this call? And you say, well, I'd like to charge it to my American Express card, or to my Visa card, or to my MasterCard, or to my SBC calling card, or my Verizon calling card. And we say thank you very much and quickly process an authorization on your card and then complete the phone call. Now, how much are you going to pay for that call? Well, whatever we want you to. And there's no obligation to tell you how much you're going to pay. So Eric's Fly-By-Night reseller service, they have a real simple billing system. It's $10 to set up the call, and then it's $5 a minute flat rate long distance anywhere in the continental United States. So when you're not at your home phone, you want to manually route the phone call to the inter-exchange carrier with whom you have signed a volume discount before you give anybody any billing information. And all of the carriers have access codes, which are of the form 10XXX. If you pick up a payphone and dial 10288, that's 10ATT, you've manually routed your phone call to the AT&T POP. And so an AT&T computer is going to come on the line saying, thank you for using AT&T. Who are you? Where do you want to go? And how are you going to pay for this? And all of them had these codes, like 10222 was MCI and 10333 was Sprint. Now, all of the codes under that scheme got used up, so they had to come up with a second tranche of codes, and all of the second group all started with 1010XXX. Now, the facilities-based long-distance carriers, these are the ones that actually have physical fibers and physical things over which to transmit your phone call. Pretty much they all got codes under the original plan, so they've got 10XXX. The ones that got codes under the 1010XXX pretty much are all resellers. Now, we've talked about two main types of carrier. We've got the local exchange carrier. They're the ones who own the central office and the wires going to your home. Then we've got inter-exchange carriers. These are the ones that connect the toll centers together. What does a reseller do? Well, a reseller doesn't have any local wiring going to your home, nor do they have any long-distance connections. What do you need to be a successful reseller? Customers and salespeople. And the idea with a reseller is that they're going to lease capacity from some facilities-based carrier, and then they're going to get salespeople to try to convince customers to route their phone calls over this leased capacity. And obviously what they're doing is buying wholesale and selling retail. Now, the profit margins in being a reseller have shrunk to the point where they really have to use tricky billing plans and things like that to make money. There are some from the big companies that are totally fine, but a lot of them, if you look at the fine print, they're just a ripoff. I was looking at one in the grocery store a while ago. It was a $10 prepaid phone card. $1.79 setup charge for each phone call. So as soon as you pick up the phone, bing, 17.9% of its value disappears. And then there was a monthly fee, and then you had to have a certain amount remaining on the card before you could initiate a new phone call. So basically you couldn't use the first part of its value or the last part. You could only use the middle part of value of this $10. 99 cents a call, or buck a call in Canada. This is one of my favorites. Hey, that sounds like a good idea. A flat rate of $1 for a phone call. But then you start thinking, well, wait a minute. What's the average holding time for a phone call? What's the average length of time that somebody stays off hook for during a phone call? Well, it's just under 4 minutes. So statistically speaking, a company selling buck a call or 99 cents a call, they're charging 25 cents a minute for long distance. I mean, why would you do that? Why not just get telephone service from the phone company? Or even get free phone service with voice over IP. Competitive long distance has kind of been there, done that. We're all familiar with this story. Competitive local services is something that's gained some traction recently. Since we have competitive local exchange carriers, CLECs, to differentiate between them and the companies that actually physically put the wires in place or own them, we often call the latter an ILEC, an incumbent local exchange carrier, the one that was there first. Now the idea here is that we're competing to provide services on the local loop. So therefore, we're not talking about equipment plugged in at the toll center. That's for long distance. We're talking about equipment that's connected onto the local loop. And in order to do things like DSL, which is one of the big drivers in this story, we have to get physical metallic access to the wires. So what this means is that the ILEC, the incumbent local exchange carrier, the one that's been there for the last 100 years, under court orders, they would be forced to go on a construction program to build a new entrance into the central office and a new wing with lights and power and place to put racks of equipment in. And then they would be required by law or by regulation to rent space in these facilities to competitors. And these facilities are called co-location facilities. And then the CLEC, the competitor, could come in and put racks of equipment in these co-location facilities and then get salespeople to convince customers to sign up with their service. Now, DSL was one of the drivers for this that made it actually happen. Covad was one of the first companies to actually start doing this in Silicon Valley. And this is before the telephone company offered DSL. Covad came to life, and all of a sudden they were offering services measured around a megabit per second for $50 a month. And what this would mean is that Covad could go into the central office in Santa Clara, California, and force PacBell to rent them space, and then sign up people for DSL, and then have a work order generated where a PacBell technician would have to unplug wires from the PacBell equipment and plug them into the Covad equipment. And this would allow Covad to offer high-speed data communications over PacBell wires to the PacBell customer for $50 a month. Now, what do you think PacBell thought of this idea? Well, within 6 months, PacBell was all of a sudden offering DSL at the Santa Clara central office as well. Now, Covad had come into the market at $50 per month for a megabit per second. PacBell entered the market with, surprise, surprise, $40 a month for the same thing. Covad's business plan had been based on getting $50 a month, and they had to drop their price to $40 and eventually went bankrupt. And as soon as Covad went bankrupt, guess what happened? The price of DSL went back up to $50 a month in Santa Clara. In any case, the idea here is that a competitor can co-locate equipment in the central office so they can get physical metallic access to the wires. In the diagram, it's drawn that the loop goes through the CLEC equipment, which is labeled DSLAM. That stands for DSL, Digital Subscriber Line Access Multiplexer. It's a box with a bank full of DSL modems in it, and we're certainly going to cover DSL in another module. But let's just say that these are the DSL modems at the telephone company or the CLEC's end of the story. It shows the loop terminating on that box and then going to the phone company. This may happen, or it may happen the other way around. Most of the time, the services are unbundled. In other words, the customer can get POTS from PAC-Bell and DSL from a CLEC on the same set of wires. So the wires have to go to both companies. You can imagine the arguments as to who terminates the wires first. Probably you as a customer would want the phone company to terminate the wires and then pass them through to the CLEC, because if the CLEC just has DSL equipment, they don't have all of the fun testing equipment that the telephone company does to do maintenance and testing on the loop. In theory, the CLEC could be providing plain ordinary telephone service as well, but that's kind of a money-losing business. DSL is the driver. For medium and large businesses, however, providing things like T1s and especially Centrex multi-line business service, that's a money-making business. So a CLEC would be interested in providing multi-line business service and high-capacity services to organizations that need more than just one phone line. For residences and small businesses, DSL is the driver. Accessing the internet over DSL was the original business model. What we're going to see going forward is doing voice over IP over that DSL connection is going to be the way that we get local voice service happening from a competitive point of view. In addition to the equipment co-located in the central office, the CLEC has to have some sort of central hub where they've got connections to inter-exchange carriers and to IP networks and the internet. And what they would do is they would backhaul everything back to this hub and then connect it off onto other networks. So they might have, if they're going to be doing voice over IP over the DSL as part of their business, they would have a soft switch sitting in that hub. Or they might just be providing plain IP service and then somebody else is providing a soft switch. And we certainly cover the story of soft switches and voice over IP in the voice over IP series of courses.